Hi, everybody. So remember last year when I told you that in Algebra 2, we review Algebra 1, and then we learn some new material? Well, in pre-calc, we review Algebra 2, and then we learn some new material. So for the first 4 weeks of school, we're going to cover about the first 3 months of Algebra 2. So hold on to your hats. Here we go with our first unit, functions through polynomials. So what is a function is our first question. To determine if something is or isn't a function, it depends on what form the function's given to you in. The first one we're going to look at is a table of values. In a table of values for a function, you have your input, which is your domain, and your output, which is your range. And what you're looking for is you need each input value to have its own output value. It can't have two output values. So this table of values you can see right here, we have a problem because 2 is an input value twice, and each time it gives you a different output value. So last year I equated that to a broken vending machine. If you put in $1 and you push A3, it should give you the same thing as if the next time you push A3. So this is not a function because the number 2 as an input value has two separate outputs. If you're given a scatter plot or a function on a graph, what you want to look for is two x values, or one x value that has two y values. So you can look at each one of these. There's an x value at -3, an x value at 1, 0, -1, and +3. And even though some of them have the same output values, that's okay. There is no x value that has two dots on that vertical line. So this one is, yes, it is a function. This one works fine. Now, if you have a graph that's completely connected instead of scatter plots, then you can do what's called the vertical line test. Again, you're checking to see if each x value represented by the vertical line has only one y value. So you run a vertical line across the graph like this, and as long as it only touches the graph in one place at any one time, then it's a function. The second example, you can see that the red dotted line touches that graph in two places. So there's one x value, it looks like it's like 2.8, and it has two output values because it touches the graph twice at 2.8. So that would not be a function. Now, if you have a equation, this one's the hardest one. You got to really think about solving for each x value and seeing if it would give you two output values. So the first one, guess it's going to give me all of them. The first one is a function. If you solved it for y, it'd be y equals x squared plus 1. Move the x squared over to the other side. Each x value, plug it in, square it, add 1 to it, and you'll get the y value. The second one, as we move across the screen, is not a function because some of the x values have more than one possible y value. So for example, if you plugged in x equals 0, you'd have y squared equals 1. So that could be either -1 or +1 for the y value. So squaring of the y is where you should watch for. That's a trouble spot. Here's one where you have an absolute value of y, the third one on this table. Absolute values for y are also a problem because you're going to have an absolute value that could be positive or it could be negative. But an absolute value of x is fine because you're only putting in one number, and you can put in a positive or a negative and it's going to give you the same output value. So absolute value on the x is okay, absolute value on the y, not okay. X squared, okay, y squared, not okay for being a function. Okay, now I'm sure you all remember the function notation. Oftentimes a function is given as f of x with the parentheses. So the input is the x, the output is called f of x, and it really is just another way of writing y, the output variable. So instead of y equals 1 minus x squared, you have f of x equals 1 minus x squared. And we pronounce it f of x. You can name it any letter you want, but f is the most common. Instead of saying what is the value of y when x equals 3, we simply say what is f of 3. That means not multiply something times 3. It's not that kind of parentheses. It means what is the output when you plug in 3. So hopefully you remember that function notation. Okay, so here's an example. This function has been named g of x, and it's a quadratic function. And we're being asked to find g of -3. So we need to plug -3 in. Plug it in. That's the input. It goes wherever x is. Don't forget, if you're squaring a negative number, it's good to put the parentheses there to remind yourself that the negative is going to be part of the squaring, not put on after squaring. And if you multiply that out and square it and add up the terms, you're going to get -2. Here's another one, g of t. Now, we're taking the same function, but we're plugging in a variable, so that's easier. You just replace the x with t. So it's going to look just like it did before, except with the variable t instead of x. Now, what if you have to put in an entire expression, a variable plus a number? Here we have x plus 2. You can do that too. Okay, you're going to put in x plus 2. You're going to square it. You're going to multiply x plus 2 times 4, and then you're going to add 1. So you're going to have to do some foiling, you're going to have to do some distribution, and then you're going to have to add some like terms to get the answer for that. But it works out pretty nicely. When you sum it all up, add the like terms, you get x squared plus 8x plus 13. Okay, there's some more practice there. If you want to plug in some other values, you can pause this video and look those over and see what you get. The challenge problem that's on the bottom of the screen is a cubic function, x to the third. Again, it's kind of time consuming to cube 2x minus 1, but it would be good practice for you if you'd like to try that. All right, now remember these, the functions that have the little bracket there? It's called a piecewise function. And a piecewise function means that there's two different parts to this function depending upon what the input values are. So our two pieces are defined for x values less than 0, so for the negatives, and then for 0 and up, so the positives plus 0. So depending on which x you choose, that helps you know which piece of the function to use to evaluate that value. So if you're plugging in 0, you would use the second one. If you were plugging in -1, you would use the first one. So f of 0 and f of -1. Pick the piece that works. Here's a 4-part piecewise function. It's got a linear, a quadratic, and then a cubic. So that would be really interesting to graph, or maybe it would be torture to graph, I don't know. So it just depends on what value you're plugging in. If we were going to plug in f of -3, we would need to use the very first piece. -2 would be the second piece. -1.2, that's a little bit tricky. That's actually between -2 and -1, so again, the second piece. -1, -1. I think that Mr. Parker threw that into this slide as a trick question. F of -1 is actually undefined. If you look at the function, it's defined for less than 1, and it's defined for less than -1 and greater than -1, but it is not defined at -1. None of the pieces cover -1, so there would be no output value for -1. -1 is not in the domain. And then x greater than or equal to 0 would work for the last function, f of 0. You could plug it in there. All right, I'm going to pause for a second here. All right. There's the work for each one of those. All right, more advanced examples of functions. We never saw this in Algebra 2, so here's a little piece of new material. Here's a function that is actually defined for 3 different variables. So it's a function that has 3 input variables, x, y, and z. Works just like the other function, except more complicated because you have 3 different things you have to plug in. So you put a 3 where you see an x, a 2 where you see a y, and a -5 wherever you see a z. Don't forget when you're squaring a negative number to put parentheses around it, because you're going to square it first. That's going to make it positive 25, and then you're going to subtract it. So minus positive 25. Sometimes on the ACT and the SAT and the GRE, which is a graduate exam, they actually like to do this little symbolic thing. I mean, somebody made up the notation for functions, and so why not make up some other notation and see if your brain can follow this logic. So here's one. Let A #B $C, so that's their notation that they made up, equal, and then they give the function. So they're asking you now to plug in for A the number 3, for B the number 2, and for C the number -5. And the way they've given it is with this box with 3 numbers in a vertical line. I mean, somebody made this up, so no problem. These can be anything. So you just plug them in. Okay, now, what if you're asked to solve for a mystery number and you're given the information in function notation? Again, no problem. You can simply plug in what you know for x and then say that the function is equal to that, and then use your algebra skills to solve for a. So you've got input and output, put them in the right spot, do your algebra. So you're going to square the 2, you're going to multiply that 4 times -3, and then you're going to do your regular algebra until you solve for a. I like these problems, just like a little bit of a 2-layer problem, I guess. Okay, now what about this one? The graph passes through a point. So that means that you've got an x and you've got a y. The 3 is the x, the output is 4a. So again, you can plug that in. There it is over there in red. Ignore the challenge for right now. So the output was 4a, the input was 3, so we put 3 for x, and again we have an equation where we can solve it using our algebra skills. There you go. All right, the challenge question has 2 parts to it because you're given 2 pieces of information. So first you plug in f of 3, and that equals 7. That allows you to solve for b. You don't know that until you try this problem, so this one was a little tricky when I went through this. And then after you get b is 7, you can use that along with the first clue that f of 1 equals -1, and you can solve for that. All right, this was a tricky one. Okay, sometimes, and I like these problems, they like to give you the graph of the function. So what a graph is all the points connected together forming a smooth curve. And so we have a lot of points represented with that blue line. Some of them, 3 of them, have been actually given to us, the coordinates. We don't know the rest of them. But if they ask us what is f of 3, what they're asking us is what's the y value if the x value is 3. So if you look on the graph and look at where x would equal 3 and go straight up, you see what point that would be. And then if you go straight across, you can tell that the y value for that particular x value would be 5. Now it's an approximate answer because you're using a graph. Maybe it's 5.00001, but it looks like it's approximately 5. So we use the approximately sign instead of an equal sign. 5, well, if you plug in 5, you see that there's an open circle. When there's an open circle, that means the graph is getting infinitely close to 5, 0, but not actually equaling it. That means there is no value at 5. So that would be undefined. And then -8, if you go to -8, we don't even have any graph over there on the far left side of the graph. So that would also be undefined. Doesn't look like -8 is in the domain of this function. It's not one of the input values that we have.